So here's my help on Unit 27, identifying equilibrium. Now let's remember that these are brackets, and brackets means molarity. It even says M, capital M. And we have a reaction over here. So if you look at this, at time zero, we have no product, and then the product keeps going up for a while, and the reactant keeps going down, which is what we would think. And that means that this is going down, the amount of it is going down, and the amount of this is going up, which means that for a while, for the first three steps and onto the fourth step, we're going more forward to the right than we are going to the left. So at 10 seconds, it's still changing from 10 to 15, and we're getting more product and less reactant. So the forward rate is greater than the backward rate. The F2 is increasing. We could have also said that this is decreasing, but that wasn't one of our options. And so is it at equilibrium? No. Now the next part is at 15 seconds. At 15 seconds, the molarities don't change. So it's going just as much to the right as it is to the left. So the forward rate is equal to the backward rate. All the molarities are constant, and it is at equilibrium. Let's talk about number 4. Now, again, we can see here, because it says that the product is orange, we had no product at first. We had only reactant. So, of course, as it goes to the right, we get less of this and more of that, until we don't. See right here, the molarities, I can't click that. The molarities stay the same after what, 6 minutes, just before 6 minutes? So at 4 minutes, it's still giving us more orange and less blue. That's more product and less reactant. So the forward rate is greater than the backward rate. That means that the product is increasing, and it is not at equilibrium. However, at 6 minutes, the molarities don't change. So the forward rate is equal to the backward rate. If these aren't changing, it's not that nothing's moving, but we're trading 1 and 1 and 1 and 1. So you might as well view it as being stopped for all mathematical purposes. Really, it's that the forward rate is equal to the backward rate. And the molarity is a constant, which means it is at equilibrium. And then we might view it like question 7. So we have A and B make AB. And it is not necessarily at equilibrium. And in fact, let's look, how many ABs do we have? 1, 3, 3, 3. So I guess it's at equilibrium once we hit minute 5. So at 10 seconds, we go to 10 to 15, we have just as many of everything as we did at 10 minutes. So the molarities of neither the reactants or the products are changing. That means the forward rate is equal to the backward rate because the molarities are constant and it is at equilibrium. So at 0, though, if you go from 0 to 5, we had 1 AB and 2 ABs, which means we're getting more product. So it's flowing more to the right than to the left. The forward rate is greater than the backward rate because AB, the product, is increasing and it is not at equilibrium. So now I'm on Le Chatelier's principle, changing amounts, and we have our classic making ammonia reaction here. You take nitrogen from the atmosphere, and you use hydrogen, which isn't that hard to get, and you can make cleaning ammonia NH3. And yes, I mean cleaning ammonia like you clean your stove with. And that takes some real doing. It takes some real heat and some effort, but it can be done. Now, we talked about the system at equilibrium, and this is at equilibrium, will flow away from the strong side and toward the weak side. And you might want to write that down. And when you change these amounts, you're stressing the system. So we stress the system by removing some NH3. So this amount went down, which makes the right side the weak side. Well, what does the products, I should say, do? It makes the left side. What does the left side do? It makes the right side. So we just weakened the ability to make the left side. whereas the ability to make the right side didn't change. That means that the strong side at the moment is the left side, and it will make the right side faster than we make the left side. So what state is NH3 in? That G means it's a gas. If we remove some NH3, what happens? Well, it decreases. That's kind of a dumb question. So what needs to change to counteract the stress? That's an odd way to say it, I think, but this has to go back up so that we get enough that it's running just as fast left as it is right. So the NH3 needs to increase similarity. And to make more of this, the forward reaction should be favored to produce more NH3. It'll make more of the right side than the left side for a moment until we all settle back down to an equilibrium. And of course, that would be shifted toward the products, toward the right side. How about question 3? We have a new reaction, and it is initially at equilibrium. And this time we added some product. So the G there means it's a gas. If you're going to add some more, obviously the amount of it, the molarity of it goes up. Now to counteract that, if you made this go up, it needs to go down a bit to achieve a new state where this is all in equilibrium again. So that needs to go down. That means that you got to chew it up by pushing this backward or to the left. You got to go this way to chew up some more of that because you artificially increased it. So the backwards reaction will happen. It will be favored because it consumes H2, and that pushes everything toward the reactants. Let's talk about Le Chatelier's principle, changing volume. And on question 1, we have again our ammonia reaction, and it's at equilibrium. So how many moles are on the reactant side? Well, what they mean is this is an invisible 1, and that's a 3. So if we had a mole of reactions, remember, a mole is just a number. So you can have a mole of anything. You can have even a mole of actions, just like you could perform an action a dozen times, you could have a mole of actions. And if we ran this reaction a mole of times, we need 1 mole of this and 3 moles of that. So together, that's 4 moles of gas molecules you would need to run this 1 mole of times total. And you would make 2 moles of product. So that's 4 moles of reactant and 2 moles of product in the balanced reaction. So then you increase the volume. Now, that's going to favor the side that has the most moles. The one that fills the space better is the one with the most moles, and this one has 4. To counteract the stress, the pressure needs to increase. We are going to assume that nothing else happens, like the temperature doesn't change, and nothing else is changing about the system. So the pressure is going to increase because now it has room to increase. Well, which one wants to increase the most? The one with the 4 moles or the one with the 2 moles? And the answer is the one with the 4, because 4 is more than 2. So the pressure needs to increase, and that will flow toward the side with the most moles, which was the left, which means the backward reaction will increase because it has the most total moles. It increases the total moles of gas in the container, and that flows toward the reactants then. Question 2, you see I got this a bit wrong because I read too fast again, but we have a new reaction and everything's at equilibrium. And the trick to this is the solids don't count for pressure. They are not gases, and they aren't even liquids or aqueous. So when it says moles of gas, be careful, that's not a gas, that's a solid. And so we have 2 moles of gas and 1 mole of gas. So the left side has the greater moles of gas that are trying to fill the container. Then you stress the system that was already at equilibrium by decreasing the volume of the container. Well, which one fits into a smaller size better? The side with fewer molecules. And that is the reactants. The products. The pressure needs to decrease to accommodate the decreasing volume that it can fit. That means everything needs to go forward because it decreases the total moles of gas because we get 1 while burning up 2. and that shifts everything toward the products. So now I'm on Le Chatelier's principle, changing temperature. And let's talk about question one. We have our ammonia reaction again, and it tells us the delta heat of reaction is a negative value, and that's kilojoules per moles of reactions. And that's what I said, you can have a mole of reactions, just like we could a plate catch a dozen times, you can have a mole of reactions happen. You can perform the reaction a mole of times. Now, this being a negative number means that the molecules are seeing the heat or the energy exit. So as far as the molecules are concerned, the heat is exiting, which means it is a product, and it is now separated from the molecules. And that means that this negative value sits over here, and we would write plus 92 kilojoules. Remember, negative tells you which side it's on. Don't write negative values. It just tells us that the negative value here tells us it's exiting the molecules into the surroundings. So that is a product of the reaction happening, and it sits then on the right as a product, so you could write plus 92 kilojoules. That means it's exothermic. The heat is exiting the molecules. That means if you run everything backward, heat is entering the molecules, and that would make it endothermic. So then we increase the temperature. That's increasing the power of the right side, because remember the heat sits over here, and if you increase the power of the right side, everything runs to the left. And if we increase the temperature, it's going to try to relieve the stress by doing the opposite. So the temperature needs to decrease, and it's going to run backward because that's the direction that soaks up the heat. The heat sits over here, and if we run it backward, the heat gets put into the new molecules that are being formed in what we would normally call the reactants on the left side. And that shifts it toward the reactants then. So here's question 3. And in this case, we see delta heat of reaction is a positive number. So we'll write plus 90 kilojoules over here. And that means that the forward reaction is taking energy in, that's endothermic, which means that the backward reaction is producing the energy. If we ran it backward, the energy would be coming out, which means the backward reaction then is exothermic. So we decreased the temperature. Now, that means we're taking the heat that's over here and reducing it. And I kind of think of it as if you weaken one side, it kind of sucks the whole system toward that side. So we're going to pull everything toward the left side. The temperature needs to increase to make up for the decrease that we just did. And that makes everything flow backward toward that point. Because remember, the heat is over here. And they point out that the backward reaction running this way is exothermic. If this way is endothermic, that means that this way is exothermic. We need to create heat to replace the heat that we removed by decreasing the temperature. And it's not that we need to, nature will naturally do this. And that will shift everything toward the reactants. So now I'm on mixed practice. And let's talk about question 1. And we have a reaction, and they're all gases. So we have 3 molecules of gas on the left and 6 on the right. And the delta H reaction is a positive number, which means the 351 kilojoules sits on the left side. So H2 is removed. That's removing something on the right, meaning everything will flow toward the right, because that's the weak side. It needs to push this back up to account for that being removed, and everything will flow toward the products. If the volume of the container is decreased, it's going to favor the side with fewer molecules. Now, I know that this looks at first glance maybe like a contradiction. I actually paused there because I got myself confused for a moment. But the volume decreased, the pressure cannot go up because you squeezed the container smaller. The pressure needs to decrease to fit in a smaller container better. And the one with fewer gas molecules is the reactants. The temperature is increased. Well, that's empowering the left side because that's where the heat sits. So everything will flow toward the right side. You're giving the left side what it wants if the heat is here. Or you could say the temperature needs to decrease to account for the increase you gave it. And like I said, everything will flow toward the products. Here I'm on equilibrium constants concepts. So we're back to talking about K, and here's the magic little formula or phrase that I said before. K is calculated by products over reactants to the power of the number in front. So K is 2.77 apparently for this, and you get that by taking the molarity for NH3 product to the power of 2 over the molarity for H2 to the power of 3, which is multiplied on the bottom by molarity of N2 to the power of invisible 1. It turns out that this reaction at this temperature, at 445 K, apparently, Kelvin, that's a different K, that's a different K. This is Kelvin temperature. The answer is 2.77 for this reaction because it is a fact. Now, anytime that these would be equal numerator and denominator, the answer would be 1, and we would say it is neither product nor reactant favored. But this is greater than 1, so that is going to be product favored. How would the concentrations of products and reactions compare after it's reached equilibrium? The whole point is that it's product favored, so we're going to have slightly more products than reactions. In other words, if this is 2.77, that's definitely more than 1, but some of these Ks are, I'm not kidding, like 10,000. So this is just a little bit more product, not an absolute shipload. For instance, here's an enormous K. So is it product or reactant favored? That's way more than 1. It is product, and it is much more product than reactant favored. Now I'm on equilibrium constant calculations. Now I'm on equilibrium constant calculations, and we have this here. The real trick to this is that water does not have a molarity in water. It is its own liquid, and it is real tempting to put it in there. And that's why I got this one wrong, because I was moving too fast and reading too fast. And I wasn't really thinking it through. So the equilibrium expression will be this to the first times that to the third over, do not put water in there, over just CH4 to the first. In which case, to get the value, we take this to the first power times that to the third power over that to the first power, and we get that, which is much less than 1, which means it is left side or denominator favored, it is reactants favored. On question 2, we have our ammonia reaction, and the K value will be that to the second over that to the third over that to the first. So then we take this value to the second power divided by that one to the third divided by that one to the first, and we get that. The only reason I got it wrong was because I misread the calculator and I didn't put the decimal in the right place, but I did it correctly. And 30 is definitely more than 1, so that is numerator favored. The numerator is bigger than the denominator if the answer is 30.4, and the numerator is the products. It is products favored. Here I have reaction quotient concepts. So here's where we do a comparison. Is this system at equilibrium? We're going to do the K math, but for the molarities as they exist right now. If you do get K, then you are at equilibrium. And when you don't, you're not at equilibrium. And we usually know that it's not at equilibrium. The question is, which way is it going to shift? Are you going to get more products or more reactants? Products, reactants. So we're going to do the exact same math. Products over reactants to the power of the number in front. And we can tell which way it's going to shift. And it's called Q just because of quotient, the dividing answer, right? So let's just say at the moment that we know the Q value is 0.363 and K is 0.0139. Q is clearly bigger. How did we get it? Products over reactants to the power of the number in front. This number is too big for the system to be at equilibrium. But the system wants to be at equilibrium. And it's going to get there one way or another, eventually at least. So the number needs to come down, right? Our number is too big. And we had products over reactants. And the number is too big. So we have too much product and not enough reactant because we need our number to get smaller, or more to the point, nature will make it get smaller. Q is bigger than K, and it will shift backward toward the reactants. We'll get less of the top and more of the bottom so that our answer Q is getting smaller and smaller and smaller until it reaches and becomes K. Let's talk about question 2. So we have an equilibrium here. K is really small. Q is bigger because bigger is less negative. So Q is bigger, and that means it will go backward toward the reactants. Okay, now I'm at quotient calculations. So like I said, it's products over reactants to the power of the number in front, just like K. So there they are. And so we'll take this one, and that is on the bottom, and we'll square it. This will be on the bottom squared. This will be on the top squared. And this will be on the top to the first power. Put those numbers in and you get that answer. But they said back up here that K was 863. And we got not even a 1. So Q is smaller than K, but it's going to become K. It will eventually anyway, at some point. So the number needs to grow, which means we need more top and less bottom, which means we need more reactants and more products, excuse me, and less reactants. It's going to shift to the right, forward toward the products. We'll try this one. K is 28.1. This will be BR squared over BR2 to the first. And what is the reaction quotient? It'll be this. See here. This on the bottom to the first, and this will be squared on the top. And I don't feel like doing it, but you can. Now I'm on explaining with K and Q, and this takes some actual explaining. Put on your thinking caps. Q is the K math, except done right at this moment, right now. It's a snapshot K. It's not done at equilibrium. It's not done at equilibrium. Not. I mean, I guess you could, but there'd be no point if you knew it was at equilibrium. So if you do Q value at equilibrium, you just get K. If K is 5 and you run all this math at equilibrium, of course you get 5. We're going to do the K math when it's not at equilibrium, and that is what we call capital Q, for quotient. I finally looked up what that is, and it just means the dividing answer. And K is for constant because at equilibrium, the values don't change. We're just going to get the snapshot value for right now. Snap. So we have, let's see, the negative delta H value that puts the heat on the right side, note for later. And so what's the reaction quotient Q? Well, it's the K math. So just for the setup of the math, just forget that it's Q and put products over reactants to the power of the number in front, and we get these. So if we remove some Cl2, that's removing some product there. Okay, get it. Product anyway. And now this gets a little bit tricky, and let's slow down. We just removed some denominator. This number goes down, and when you divide by a smaller number, you get a bigger answer. So the value of Q just increased. That doesn't change K. You might want to write this down. K is only affected by temperature. Now, they said at the beginning it was initially at equilibrium. So it was at equilibrium and Q used to be equal to K, but we just increased K, which means it's now bigger than K. So we have too much. We are not at equilibrium. Our answer is too large to be at equilibrium. That means we have too much PCl5, we have too much product, which means we have too much numerator, right? Too much product, too much numerator. And so we need to get more reactants, more left side. And so it will shift toward the reactants so that it can settle back down to equilibrium. So the container volume is decreased. If the volume of the container gets bigger, it favors the side with more gas molecules, 2 versus 1. So it's going to shift to the left, which makes us have a bigger denominator. And when you divide by a bigger number, you get a smaller answer than before. But we didn't change the temperature, so K doesn't change. Q is now smaller than K, which means our answer is not big enough. Our number is not big enough. We need more numerator, and the numerator is the product. So it's going to shift toward the products. The temperature is increased. I said that's going to change K, right? And let's see how. The effect on Q. Well, you know what? We didn't change the molarity, so the Q values don't change. But what happens if we put in more heat? We said the heat sits over here, and that's empowering the right side, so the whole thing flows toward the left. These numbers go up, this number goes down, this number goes down, this number goes up, and your answer gets smaller. Since that didn't change, Q is now bigger than K because K went down. Our number, Q, at the moment is too big to be at equilibrium. It's too big. That means we have too much numerator and not enough denominator. We need more of the left side and less of the right side. We need it to flow toward the reactants, or it will flow toward the reactants. Here's question 2. To set up our Q value, it's products over reactants to the power of the number in front. There we go. And our heat is a positive number, so it sits over here. So we removed some reactant, and that makes the denominator go down. If you divide by a smaller number, the answer gets bigger. But we didn't change the temperature, so K didn't change. This got bigger, that didn't change. Q is bigger than K. We have a number that is too big to be at equilibrium. To go back to equilibrium, which is what it's going to do, we need to get less numerator and more denominator. It's going to shift, so we get more of this and less of that. Is going to shift toward the reactants. On the second line here, they are wrong. The container volume is decreased. The volume is decreased, we have less space, and it favors the side with fewer gas molecules. So this number is going up, that number is going down, and the answer then goes down, and they are wrong, which means all the rest of this turns around, and they made a mistake. So for the third line, the temperature is decreased. We said the heat is over here, which makes everything kind of get sucked over to that side. This number is going up. These numbers are going down. These are going down. That's going up. The answer is getting smaller, but we were really talking about K because changing the temperature doesn't change the molarities. So the Q values don't change, but the K value decreases, which means Q is now bigger than K because that didn't change and that one got smaller. And our number is too big. So we need less numerator and more denominator. And that makes everything flow to the left. toward the reactants.